Okay, today we are going to talk about section 9 through 10, mainly focusing on electron configuration. So the first thing we're going to look at is just electron arrangement of the first 18 atoms, and then we'll take that pattern and apply. Okay, well, electron configuration is just a way to represent electrons. It shows their arrangement, what energy level they're located in. And so for hydrogen, this is 1s1. Okay, so we know that hydrogen is the first atom. It's got one electron, and it's going to be in the lowest energy state. So 1s and then a superscript 1. We can also draw what's called an orbital diagram or a box diagram. We represent the orbitals using boxes that are grouped by sublevels, so S, P, D, or F, and then we use the arrows to indicate electrons. And if you remember from the Pauli exclusion principle, they have to spin in opposite directions, and there can't be more than 2 electrons in an orbital. So for hydrogen, we have one box because it's just in the 1s orbital and it has 1 electron, and so we draw 1 arrow. All electrons start at the 1s orbital first because it is the lowest energy level, and so we're always going to fill lowest energy to highest energy. So everything will start at 1s. And so for the first 18 electrons, we're going to occupy 1s, 2s, 2p, 3s, and 3p sublevels. Okay, so in general, here's how you're going to write your electron configuration. You'll have your element symbol, whatever we are trying to find electron configuration for. Your 1 will be your N, that'll represent your energy level. Your letter will represent the orbital, and this superscript is the number of electrons in that orbital only. And so S can only go up to 2, since each P holds 2 electrons and there are 3 sublevels or 3 orbitals, then we could have a total of 6 for P. And we'll talk about that as we get there. Okay, so here's how electron configuration is arranged for the periodic table. If you notice, we're starting with 1s because it's the lowest energy, and then we just follow everything across, kind of just like you would read a book. Okay, and so everything is in good order until we get about here. We have 4s, and then we go to 3d. And so that's just kind of something that you have to remember. Okay, so let's start looking at other elements. So helium is located up here, and so it's 1s2. Because remember, each sublevel or orbital can hold 2 electrons, and since 1 only has s, and we have 2 electrons, then this is a 2. And if we were to draw the orbital diagram, we'd label it 1s. And because helium has 2 total electrons, one has to spin up and one has to spin down, or clockwise and counterclockwise. Okay, let's look at the next element, which would be lithium. Lithium would be located right here. Okay, we're going to start from the top. We have filled up the 1s because now we're at 2s. So we have 1s2 because we filled it up, and then we go to the next sublevel, which is 2s1. And if you count all of these superscripts, you should get the total number of electrons, which in this case is 3. So the 1s orbital was full, we went to 2s. If we draw the orbital diagram, remember I want a box for every orbital. So 1s, and it's full, and then 2s, and since there's 1 electron, I draw 1 arrow. Okay, let's go on to the next element, which would be beryllium. Okay, beryllium has 4 electrons total. 1s is already full, so it gets written as 1s2, and then we're also going to fill the 2s because we're right here at the end of that 2s, and so we're going to write 2s2. And if we add these up, we get 4. Okay, so if I were to draw the orbital diagram, my 1s is full, and it gets 2 arrows, and my 2s is full, and so it gets 2 arrows. Let's move on to boron, which is the next one in line. Now we have entered 2p. Okay, well, I still need to start at 1, or the lowest energy level, so 1s2 is full, 2s2 is full, and now I'm going into 2p, and it's just 1 electron in that 2p, because I have 5 total. So I want to draw a box for my 1s, I want to draw a box for my 2s, and this one is full, and this one is full. Now 2p is a little different because it can have 3 orbitals, so I want to draw them connected, because remember it's a box per sublevel. So here's my 2p, here's my 3 orbitals, and I'm just going to put 1 electron because that's the number of electrons in 2p. Traditionally, you want to put it in that first orbital. You know, technically you could put it in any of the 3, but traditionally it goes in the first one. Let's look at the next element, which is carbon. Okay, so for carbon, we are right here. 1s is full, 2s is full, that's 4 electrons. I have 6 total, so I need 2p2. So same idea as above, 1s, 2s, 2p, 1s is full, 2s is full. Now, 2p has 2 in it. I want to fill each orbital with 1 electron before I start doubling up. And so if that's the case, then I want 1 in the first orbital and 1 in the second orbital. Okay, before I start doubling them up, each one wants 1. Okay, let's take a look at nitrogen. Nitrogen is the next one over. So now we have 3 electrons in the P's. S is going to look the same. 2s is going to look the same. 2p, because there are 3 electrons in the 2p, I can fill each orbital with 1 electron. Okay, and let's look at oxygen. Again, same thing. We're just moving 1 more over. Okay, 1s is full, 2s2, 2p4, because if I added all of these up, I would get 8. Okay, so my 1s looks the same. My 2s looks the same. Now my 2p, I've got 4 electrons total I need to distribute in the 2p. So I want to do 1 per box first, 1 per orbital, so 1, 2, 3. Now I still have 1 more I need to use up. So now I can start doubling up, starting with the first orbital. Okay, so fluorine is located here. Now I've got 1s2, 2s2, 2p5. So here's my 1s, 2s, okay, 2p5. I've got 1, 2, 3, 4, 5. Okay, let's look at neon, which is 1s2, 2s2, 2p6. You notice, I always know I have 2 electrons in 2s because if I count the number of elements that are located in the s, I have 2. If I look at the p's, there are 6 elements here, and I've got 6 electrons or 3 orbitals within the p. So neon is at the very end. It's a noble gas, and it's at the end of the 2p column. And so what that means is my 1s is full, my 2s is full, and my 2p, because I have 3 orbitals and each one can hold 2 electrons, my p is also full. 1, 2, 3, 4, 5, 6. Remember, the thing about noble gases is that they don't react with other things, and that's partially due to this. All of their orbitals are full, and they want to be full. Full means stable, and so they're already stable. They don't need to bond with anything else to get electrons. Okay, let's look. Now we're going to go down to sodium, which is located right here. Okay, so we have 1s2, 2s2, we filled the 2p6, and now we're going to the next energy level, which is 3s1. Okay, so 2p was full, we go to 3s. Now, you may have noticed that these are getting really long to write. Well, there is a shortcut, and it's based on the previous noble gas. Now, the only one you can't use is helium, so up until neon, you have to write the whole thing. But after neon, you can use neon and other previous noble gases to shortcut it. By writing neon in brackets, it's basically like we're writing all of the electron configuration for neon. And so we just skip writing all that and go on to what's after neon, which is the 3s1. So if I was going to write the orbital diagram, I could still do neon in brackets. And then I know all s's have 1 orbital. And so I'm going to label it, and because it's 3s1, it gets 1 electron. Magnesium is the next one over. We're right here. Okay, so now I'm filling the 3s orbital because I have 2 electrons in there. And remember, this part is equal to neon. So I can write Ne, and then 3s, and because it's 3s2, I have 1, 2. Okay, we will discuss elements 13 through 18, but they basically follow the same identical pattern. We're just going to keep adding electrons going from S to P. Okay, so let's look at some other important terms. Valence electrons are the electrons in the highest or the outermost principal energy level. Okay, and they are the ones that are involved in bonding with other things because they're located on the outside. So if we look at nitrogen, we have 1s2, 2s2, 2p3. 1 is a lower energy level than 2. So we're looking at anything that contains the highest principal energy level. So that would be 2s and 2p. And because I've got 2 as my subscript for 2s and 3 as my subscript for 2p, that equals a total of 5 valence electrons. This is going to become important when we talk about Lewis structures. Let's look at sodium. We've got 1s2, 2s2, 2p6, and 3s1. Well, our highest principal energy level is 3. And so 3s1 is where our valence electrons are located. And because I have a 1 here, that gives me 1 valence electron. Core electrons are the inner electrons. They are not involved in bonding, they just fill those lower energy level orbitals. Okay, something to notice about and this is how this relates to the periodic table. Atoms of elements in the same group, so the vertical organization, have the same number of valence electrons. So except for helium, but helium has a full outer shell of 2, and then the rest in its group have a full outer shell of 8. So that just depends on the number of orbitals. So it's still the same idea, maybe just not exactly the same number, unlike all the rest of the groups. Orbitals are in different principal energy levels, but the number of valence electrons is the same. Okay, so that just number of those outside electrons is the same for everything in that vertical group. And this means that they also have similar chemical properties. So remember, the periodic table is based on similar chemical properties. So anything in that vertical group is similar. So, for example, lithium and sodium, their final, or their valence electron configuration is 2s1 and 3s1. So even though they have different principal energy levels, their total number of valence electrons is the same. Okay, so if we look at atoms with more than 18 electrons, they don't follow exactly the regular pattern, and that's the D part that I talked about at the beginning. And so let's look at potassium, which has 19 electrons. We would assume that we would go to 3D after 3P, because D is the next part. We're getting close to transition metals. Okay, but K belongs in group 1, so it must end with 4s1, because it's in that very first group. And so potassium's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. All of this is equal to argon's electron configuration. So we can shorthand it by writing just argon and 4s1. And if I did the orbital diagram of that, I would do argon, and then I know all s's have 1 orbital, and this one has 1 electron. Okay, if we look at calcium, we're adding another electron, so it's argon 4s2. Okay, so now the 4s orbital is full. Okay, because remember, any s can only hold 2 electrons. And so now we want to go to 3D, which is where the transition metals are. And then if you keep following that map, we go then to 4P. There are a few exceptions within the 3D, and this follows for anything that's below chromium and below copper. Normally, we would say that they would do 4s2, 3d4. But the problem with that is because D contains 10 total electrons, shells that are half full or completely full are the most stable. And remember, all elements want is to be stable. And so what they'll do is take an electron from the S and give it to the D, making it 4s1, 3d5. So now that outer energy level, or the 3D, the last one we write, has 5 electrons instead of 4. It makes it more stable. So just a couple things to consider with transition metals. Okay, so we said that elements with a particular type of valence electron configuration all show similar chemical behavior. So anything in this group 1 all has 1 valence electron, so they're all similar in chemical properties. Group labels for groups 1 through 8 indicate the total number of valence electrons. So you can see we have a 1A here, a 2A, and then over here we have 3A, 4A, all the way up to 8A. Okay, these are called main group elements or representative elements. You can see it labeled right here. So we're basically not including the transition metals. And so those group numbers tell you the number of valence electrons. So you don't have to go through and write the electron configuration every time you want to find valence electrons.